If you're familiar with Reddit, basically we're a very large-scale social media site. We have a lot of infrastructure. We run on Kubernetes. We use Prometheus. We have a lot of Python, and we also write a lot of Go. And we serve quite a lot of requests. So early on, we had a lot of Python services, and they're serving billions and billions of requests per day. And if you're familiar with Python, you end up with this problem where you have a global interpreter lock, and you can only serve a certain amount of requests per second per process. And so in order to scale, you need a lot of processes. So we add Kubernetes, and now we have thousands and thousands and thousands of pods, many, many pods. But that's still not enough, because you just run out of, Kubernetes can only spin up so many pods before it starts to crumble, and also all your other infrastructure can't monitor all that. So what we wanted to do is we wanted to go back to how we did things on the virtual machines, which was we ran multiple processes per worker instance. And so we had used Einhorn in the past, and then we switched off of Einhorn, and then we switched back onto Einhorn. And Einhorn is a multi-process worker controller, but it does one cool trick, which is it uses SO reuse port in order to do the load balancing across multiple workers in the same instance, or for our case, the same Kubernetes pod. And this worked reasonably well, but we were seeing a pretty bad long tail latency. And so I started doing some investigation and found that using some TCP dump and watching the traffic, and discovered that there's kind of a bit of a queuing problem where a couple of different connections would go into the same Python process, and they would just overload each other. And other Python processes in the same pod would be basically idle. And so we were like, hey, we need to figure out how to do better load balancing in our Kubernetes pods. We also had other resource problems. We started looking into thinking about, like, okay, so what should we do with this? Well, the Einhorn project at the time we started working on this was archived. Thankfully, it got picked up, and if you want to use Einhorn, go for it. But I think our replacement solution is better. Einhorn is also written in Ruby, and so we would have to have both a Ruby interpreter and a Python interpreter in the same pod, and that seemed like kind of annoying and a waste. And we also had to do some weird hacks to do things like, in the background, we wanted to restart all the worker processes. And so instead of, and Einhorn really didn't have a facility for that. So we ended up doing using Kubernetes shell probes to both provide the readiness check and every once in a while restart all the workers. It was a weird solution, but it works. But we wanted to do that in a little bit better way. We also wanted to get rid of the random load balancing with SO reuse port and actually put a proper load balancer in front of those workers. And so now we built Monoceros. And so Monoceros is a multi-process application controller written in Go. It has some good observability tooling built in. It allows us to do different load balancing with and we're running it at full scale, running some of our biggest core services and adding a few more services. Every few months, we onboard some of our other legacy services that get more traffic. And so now I'll hand it over to Sotiris, who can talk about how we built it.
Awesome. Hi, everyone. So I guess Ben laid out the requirements of what we want to do, but then the challenge is, how do you deploy such a system in like large organizations such as Reddit with all your biggest services relying on it? So we decided, what is the minimum viable product that would allow us to first collect data? This is really important because it allows to know if we messed up something in the deployments or if we introduce a regression. So observability and data was really important for us. And the second thing that we want to do was also add some features that would add value to our customers. So we decided not to tinker with the data path at all for the MVP. So we still relied on SO reuse port. So we copied all the features from Einhorn that were useful for us and re-implement them in Go. And we also, as additional features, we had better observability. So we had Prometheus metrics generated by the supervisor, Monoceros. And also we had limiters to combat memory leaks. So we knew some of our applications were leaking memory. So we knew that we had to periodically restart the workers. So we thought, let's make this a first-class primitive inside Monoceros. And to see a bit of how Monoceros looks like and the API surface, here is a greenfield adoption and like how the configuration looks like. You just specify basically the application that you want to run, how many replicas you want to run, how often do you want to restart it, and what is the max restarts. And from there, Monoceros takes over and controls the application. And here you can see the first thing, which is the minimizing the effects of memory leaks. You can see on the left, this is our applications leaking memory. So every night when people stop deploying code and pods stopped recycling, we start ballooning into memory. At some point, we start showing some kills from Kubernetes. And then the next morning, we just do another deployment. Our memory goes back to baseline, and this kind of like repeats. You can see in the middle of the chart, it kind of gets worse over the weekend. Somewhere around here, where we have like a long weekend, it's get worse. And as we deploy now Monoceros into this fleet of pods, we can see the amplitude shrinking and the effects basically of periodically restarting workers to manage the memory. I think this change in aggregate across our fleet was approximately 1 terabyte of memory in saving across our entire fleet of pods. And the second thing, which as we said, Ben said before, that some workers were working quite a bit and others were staying idle. Before that, we had to do it with TCP dumps. Now we can actually have the observability to see it. So Monoceros collects CPU metrics per worker. So we're able to see what the P99 and the P50 worker, how much CPU they're using. So now we see pretty high standard deviation, and that allows us to motivate the further investment of like, let's change the data path, let's change the load balancing between the workers to make it more efficient. So here we go, more features, and let's change the data path. So here we have Monoceros running now in proxy mode, which is essentially the same diagram as we saw before, with the only difference being that instead of SO reuse port, we have a full-fledged proxy load balancing the traffic. We chose Envoy as the proxy. And the reason for that was that in our use case, we also care about thrift traffic. So we want to be able to load balance between workers that do thrift as a protocol. And Envoy is the only out-of-the-shelf load balancer that can do thrift load balancing. So it was a good choice for us. Additionally, there is quite a bit of overhead in managing an external process as an application. Given that Monoceros is already a process controller, we had already a lot of the things, a lot of the abstractions inside the code to do that effectively. So for us, proxy is essentially another worker that we need to manage. So we had a lot of the abstractions in the code already. And we also wanted to tighten up a bit of like our local unit integration tests. Monoceros as a system is fairly well tested in isolation. So we want to make sure that we can deploy with confidence and without incidents, especially as we change the data path, which is really critical for our applications. So now we're going to see a high traffic service and like see basically the results that we had from this deployment. So this service, we measure like the latency, the P99 latency by our NGINX ingress controller. And this is week over week charts. Green is after we deploy Monoceros. We deploy Monoceros here. And yellow is the week before that. So we can see a 20 to 30% reduction in the P99 as measured by the NGINX ingress, which is like external to the application. And then we also want to measure the latency besides the P99, which is more of like the tail latency measured by the NGINX. We also want to see the average latency to see if the average case is also improved. And both the average and the tails tell a similar story. We have like similar time on the deployment. We start seeing like this improvement, which is great. But at the same time, when you're seeing things from the NGINX ingress or from your ingress, you see all the requests. And we know that for the business, and as you use Reddit, not all requests are equally important. For example, the request that you use to load your home feed the first time you open the app is quite more important than other requests because it's core part of the user experience for pretty much everyone. So we start measuring the P19 latency of critical requests. We use this as an example, a request that's part of the home feed query. And now we see the measurement inside the application, and we see the 10% improvement in latency at the P90, which is great because this can actually translate it into a really better user experience, And now this is the charts that we showed before with the CPU utilization before and after, and you can see how these lines essentially became like closer together, and how now the most loaded workers are less loaded, and how the least loaded workers are more loaded. So this shrinkage allows us to have like more predictable CPU usage among our fleet, and allows us to scale in a more predictable way and set our CPU limits and CPU utilization, push it a bit higher, because predictability is really important when you want to scale. And I think that's basically my favorite chart for how to use Monoceros and the effect that it had. Where before we had the same application, it was leaking some sockets, some file descriptors, and we can say that it does it in an unorganized, chaotic way. Different workers, some workers are leaking way too many sockets, some are sitting idle. And then after we move to Monoceros, we see the same type of problem, but in an organized, in a more well-behaved way. And then you can see all the workers getting equal amount of traffic, they're still leaking the same sockets. And then you can see the effects of staggering restarts where each working is being resetted. It goes back to 0 and again.
Yeah, and one of the things you can really see here is the effect of the random load balancing causing kind of the birthday paradox, where you get hot connections all hitting the same one, and some of them are accelerating and have a very high leak rate because the traffic is just not balanced between the workers within the pod. So the thing that we discovered is not only do you need really good cluster load balancing, you also need good pod load balancing for queuing.
Awesome. Yeah, and so that's basically a summary of all the results and what we were able to achieve by using the in-process, basically in-pod load balancing to remove this queuing effects and the effects that it had like on latency. Yeah, and we're gonna open source Monoceros to the world. So we believe that if you run a Python, or Ruby, or Node service, Monoceros can help you. And with that, I'll pass it over to Ben, who's going to talk a bit more about some other features that we're thinking about adding.
Yeah, so we also want to add a bunch more observability features to this. For example, we have some legacy services that the dev teams don't want to re-instrument. So we currently run statsd as a sidecar, so the Prometheus statsd exporter is a sidecar to our pods. But we can pull that functionality out of the sidecar and eliminate a sidecar by putting the exporter directly into Monoceros. And we also were thinking about like what can we do to improve the load balancing and even shrink that the standard deviation of CPU so the workers are even more balanced, because the more balanced the workers, the higher we can load them up and the fewer pods that we need to run, and that saves us memory across the fleet. Plus, there are scaling effects where as you load up the Python, it gets slower and slower due to the contention of all the different things going on. I think a lot of our Python workers are using G-event, so we can do a bit of multi-process working, but you end up having this problem where one G-event instance is waiting on another, and you get this stacked queuing effect. And you get the teller problem with individual Pythons. And that's it.